Shut up. Okay. So if somebody wants to get, well, you can get the lights if you want. If you are happy with this, that's fine. So we have kind of done the first two steps of our compiler. And we've done it basically in the, we had this little made-up language from an introductory chapter. And we saw the problem at the end of last class where we really need to have some sort of tokens that separate statements. So we're going to start looking at chapter 2 of the book now, which really talks about creating what we've already started creating, but for a Java language. That is a language that has semicolons at the end of the lines. So we've already been moving in this direction anyways. So in 3 through 6 of this book, we're going to write these individual parts. So we'll kind of gloss through 2 pretty quickly just to kind of catch us up to where we are now. So I'll just read through this and we'll look at the example code and then go through as quickly as we can. So we're gonna, the chapters 3 through 6 will illustrate the techniques by developing a working Java program that translates representative programming language statements into 3 address codes. That is assembly code, 3 address assembly code. An intermediate representation. In this chapter, so that's kind of like Java bytecode. So think about how the Java compiler works in the first place. The Java compiler compiles into Java bytecode, which is a low-level language understood by the Java virtual machine, which then translates that low-level language into a native language on the CPU. In this chapter, the emphasis is on the front end of a compiler, in particular on lexical analysis, parsing, and intermediate code generation. Chapter 7 and 8 show how to generate machine instructions from 3 address code. We start small by creating a syntax-directed translator that maps infix arithmetic expressions instead of postfix, infix. Postfix would be like plus 2, 3. Infix is 2 plus 3. Do any of you, do they still make the Hewlett-Packard graphing calculators?
Texas Instruments really owns that.
Okay. Well, yeah. When I was younger, it was like a competition between the two. So like the HP people were kind of like Mac people, and the yeah, I don't think they took off, did they? So you had the TI people those were like the PC people, and then you had the Hewlett-Packard guys that were like the Mac people that thought they was better with the postfix and everything like that. And so I learned how to program on an HP graphing calculator because that was supposed to be the next big thing. They were extra expensive and blah, blah, blah. And no, they didn't take off. But that was an interesting start.
It's kind of dumb that
I might have I might have one somewhere.
high school still require them when you can get like an app on your iPhone that can do everything that they can do for like $1.
And they still require you to have an act.
My brother had to buy one.
You can't use your
Can't use
phone
your phone in class. So you gotta have a $100 calculator to do the exact same thing.
Text message here.
Okay. So they already give us a working program. So as you're doing homework and you need examples, you can look at Appendix A. But we're going to write it from scratch. We're not going to use their examples to write it. So ours very well might look different. So you can do this in whatever language you want. Okay, so as a starting point, this is what our syntax might look like here. Now notice right from the beginning, they are already making our language a little bit smaller. So they're saying the global world here is a world containing a block statement. So notice it doesn't say public class and that kind of stuff. Those are things we can add in later. But we're moving towards a bigger language, but still a subset of the pure Java language. That makes sense? But notice we are dealing with a language with semicolons, separating statements. So they're showing us situations where you have a bunch of statements on one line, separated by semicolons, and that kind of crap. Okay. Where last time we talked a little bit about what if we didn't have semicolons. Now it becomes important with indenting and things like that. A good example of a language where indenting is very important is Cobol. Any of you ever seen Cobol? Cobol, your program is divided up into something called paragraphs. And paragraphs have to start on specific indent to certain lines. And it's important that you indent to a certain place in order for it to know where to start. So it's very interesting.
It sounds bad.
What's this?
It sounds bad.
Cobol? That's what Tabby does every day. She sits there.
She got so sick.
It is why she got so sick, probably. Let me zip to...
Made her think she had a fever, but she just wanted to get out of work.
Okay, so we've already done part of this. So we've written a lexical analyzer for a simpler language. Create a token stream. As part of the lexical analyzer, we create a symbol table. We've parsed it into a syntax tree. We haven't really used that syntax tree yet, and really our syntax tree right now only works for single statements, where we haven't even defined what a statement is. So it works for single line programs for right now. Okay, so that's our output right here. So we're kind of up to this point, but we're going to go back through and not redo, but upgrade these sections to work for a more modern-like language. Okay, so let me think about the way we want to approach the tree structure. Trying to decide how much of this I want to skip. Question is, do we skip this whole chapter? I think we might want to. Because this chapter will actually kind of be not fun.
Yeah, you hate not having fun.
That's kind of what I was thinking. Just talking about postfix. Okay, let's do that. Let's start with parsing. We'll skip all this stuff that's up here is basically the stuff we talked about last semester in programming languages. Context-free grammars and that kind of stuff. We pretty much remember those things, or at least have a fighting chance. Okay, so parsing is the process of determining how a string of terminals can be generated by a grammar. Grammars being our step of rules for a language. In discussing this problem, it is helpful to think of a parse tree, blah, 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 being constructed. Even though a compiler may not construct one, in practice, however, a parser must be capable of constructing the tree in principle, or else the translation cannot be guaranteed correct. We are creating parse trees. We're calling them syntax trees, but we're going through token by token by token, which are that's parsing out of our parsing our program, and we're creating trees out of those. Okay, so we're going to talk about something called recursive descent for creating our parse tree, and you're actually going to see that it's already similar to what we're already doing. So this can be used to both parse and to implement syntax-directed translators. A complete Java program implementing the translation appears in the next section. Again, we're not going to use their code. We're going to write it ourselves. There are some things. One of them is called a yak. There are pre-existing tools that you can use to create your own programming languages, rather than writing it from scratch like we're doing. They're not friendly programs to use, but they do create the symbol tables, they create the lexical analysis, they do the different parts that we are doing, but they do it in a generic sense. So you create some configuration files and tell it, okay, I have this, this, and this, and you fill out all those configuration files, run it through your syntax, and it will create for you the output low-level language type thing. So, for any context-free grammar, there is a parser that takes, at most, big O notation, n to the third times to parse a string of n terminals. But cubic time is generally too expensive. I'm not sure that's even a fair statement, seeing as though compiling, we don't necessarily care how expensive it is. But we'll keep going. Fortunately, for real programming languages, we can generally design a grammar that can be parsed quickly. In linear time, algorithms suffice to parse essentially all languages that arise in practice. Programming language parsers almost always make a single left-to-right scan over the input, looking ahead one terminal at a time, and constructing a piece of the parse tree as they go. Okay, so this is going to be a change with how we're doing our parse tree. This goes back, historically, I don't know if we've really talked about it here, but we've definitely talked about it in other classes, single pass versus multi-pass compilers. Old compilers made a single pass. And because of that, that's why header files exist, for prototyping functions and things like this. They're talking about an algorithm where we can even make a single pass, but our tree, the creation of our syntax tree, is more efficient because we're actually looking, they're calling them terminals, we can call them tokens. We're looking one token ahead as we're reading. So before we process the token we just read, we're going to look at the next token, and the next token helps us know what's coming next. That make sense? Okay. So most parsing methods fall into one of two classes, called the top-down and bottom-up methods. These terms refer to the order in which nodes in the parse tree are constructed. In top-down parsers, construction starts at the root and proceeds towards the leaves, which is what we've done so far. While in bottom-up parsers, construction starts at the leaves and proceeds towards the root. The popularity of top-down parsers is due to the fact that the efficient parsers can be constructed more easily by hand using top-down methods. Bottom-up parsing, however, can handle a large class of grammars and translation schemes, so software tools for generating parsers directly from grammars often use bottom-up methods. So that was those things like yak up here. So maybe the punchline is automated syntax tree creators are often going to use a bottom-up approach. It's not something humans easily visualize, but it's something that algorithmically is not that difficult once you write it. But it's difficult to write it because it's difficult for humans to visualize it. Make sense? So we're top-downers. That's what we are. Top-down parsing. So we consider the grammar that is well suited for this class of methods. Later in this section, we consider the construction of top-down parsers in general. Grammar in figure 2.16 generates a subset of the statements of C or Java. That's the deal that didn't have the public class crap, just had the block structure. Okay. We use the boldface terminals if and for the keywords if and for, respectively, to emphasize that these character sequences are treated as units, i.e. as a single terminal symbols. Eventually, we'll throw methods into that same category. Further, the terminal expression represents expressions. A more complete grammar would use non-terminal expressions and have productions for non-terminal expressions. Similarly, other is a terminal representing other statement constructs. So this is taking our language one step further. In our simple language we've done up to this point, we've had identifiers, operators, and other. Well, we identifier, operators, and literals, right? And really, as far as our tree went, we dealt with them as operators and non-operators. Well, now we have things that go even deeper than that because our language is getting more complex, and it's still a small subset language. Okay, the top-down construction of a parse tree, like the one in 2.17, is done by starting with the root, labeled with a starting non-terminal statement, and repeatedly performing the following two steps. So, before we look at those steps, let's go to 2.17, because this is going to help us answer that question that we talked about last class, whether or not each statement belongs in its own syntax tree or not. 2.17. This is this guy. So we have a statement. Statement has a terminal for, open parenthesis, the first op. I'm trying to decide what is this op expression. Op expression. Okay. So that's an op expression. I don't know why they put a T in there. Followed by semicolon, followed by an op expression, followed by semicolon, followed by an op expression, followed by closing parenthesis. Okay? So this is our typical for loop, right? So from this language, op expressions come in the category of like int a equals 5. Op expressions come into the category of things dealing with Booleans, right? Boolean expressions. And op expressions fall into the category of things like I++ and a equals a plus 2, that kind of stuff. So really, op expressions are pretty generic type of expressions in the language they have here. But now notice that we have a top-level statement. And within this top-level statement, we have other statements. So we want to think about our trees as being collections of statements. But does that mean that a single tree holds on to all of our statements? Or does that mean that we have multiple trees that each hold a statement? So that's what we're going to find out. So coming back up here. So here's the two steps. At node n, label with a non-terminal a, select one of the productions for a, and construct children at n for the symbol in the production body. What does that mean? Well, it means that we just saw something that's a statement, therefore it follows the rules of a statement, so we need to construct a node, label with that guy, where the children at that node are the part of that production, the rule in our grammar. So our grammar is going to say, well, if this is the for statement, for loop, it's going to start with the word for, followed by an opening parenthesis, followed by an op expression, followed by another op expression, followed by another op expression with semicolons in between them. Once we know we're in the right type of thing, we're going to create a brand new terminal, a brand new node in our tree, and build out that expression because we know what belongs. Okay? When we see our grammar, when we have our language defined to us, as soon as we know what we're dealing with, we know what it's supposed to look like, ignoring white space and things like that. Does that make sense? So in Java, a for loop always looks the same at the syntax level. Sometimes our op expressions are more complex than other op expressions, correct? So in Java, we can have comma delimited op expressions. That is, we can say int a equals 5, comma b equals 7 as our starting point in a for loop. We can have Boolean expressions, and what's a Boolean expression? Any expression that boils down to a single value of true or false. They can look like very, very simple expressions, and they can look like monsters. Make sense? Similarly, op expressions could be a++, comma I++, comma C minus minus. So you can have a comma delimited op expression as well. So for loops support all that. Most of the time, we have a for loop that looks like something like for int I equals 0, I is less than such and such, I++. We're only using the simple version of our op expressions, but an op expression really could fall into many different categories. So we could have a grammar of op expressions, where that grammar has several productions, several rules. And each of those rules might say, well, an op expression could look like this, or an op expression could look like this, or an op expression could look like this, so on and so forth. Can that make sense? So we have the collection of statements, where a statement can look like a for loop, where a for loop looks like this. The word for, followed by an open parenthesis, followed by an op expression, followed by a semicolon, followed by an op expression, followed by a semicolon, followed by an op expression, followed by a closing parenthesis, followed by a statement. What's this statement? This is a question that goes back to your first semester of programming when you first learned about for loops and if statements. Something that ends with a semicolon?
Yeah.
Is that what you meant?
That's what I mean.
Okay, so that's the wrong answer that you meant. Okay, got it. Not completely wrong. Many statements end in semicolons, but not all statements end in semicolons. Let's see. Anything that ends in a semicolon is a statement, but not all statements end in a semicolon. This gets back to our discussion about curly braces. When I first taught you how to write if statements or loops, I said you always should use opening and closing curly braces. It's never wrong to use an opening and closing curly brace. Remember this discussion? Okay? But technically, you can write an if statement and you don't need an opening and closing curly brace because an if statement operates. So if some Boolean expression is true, perform the following statement. And what comes down to is whether or not you understand what a statement is. So if something is true, if you want to do this, and each one is an individual statement, you need to package those two statements into one big statement. That's where the curly braces come in. Okay? Because if statements, for loops, these guys all operate, well, they all fire a single statement when the Boolean expression is true. Single statement can be one statement, or it can be, pretty common for us, a block notation, opening curly brace, closing curly brace with with 0 or more statements inside. So a block structure is a garbage bag filled with 0 or more statements. Does that make sense? That's why it's never wrong. It might be syntactically inefficient, because now we have to parse it, we have to account for it. Does that make sense? But it's never wrong to have an opening and closing curly brace. So that's what this guy right here in our syntax tree is. This is the body of the for loop, where this statement is going to follow the rules of the statement grammar. What are my possible statements? Well, you can have a for loop. You can have an if statement. You might have an assignment statement. Blah, 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 as our language gets more and more complex. So you have the grammar. So right in this, just from this little tree here, we have a language of statements, whereas the only one they're showing us right here is this for loop. But we know at the very least that one statement exists, a statement that's called the for statement probably. And we know that these animals called op expressions exist. We know that they exist. We're not necessarily sure what they are yet, because we know that they're either this, or this. So an op expression could be an expression, it can be an expression, and I'm guessing this is their little shortcut for assignment. But we'll find out. Okay, so we don't necessarily know what the grammar for this guy looks like. We can see our grammar, oh actually we do. We do see what our grammar looks like right up here. So here's our grammar. We have a statement. A statement can be an expression followed by a semicolon. It can be an if, followed by an opening parenthesis, followed by an expression, followed by a closing parenthesis, followed by a statement. It can be a for, followed by an opening parenthesis, followed by an op expression, followed by a semicolon, followed by an op expression, followed by a semicolon, followed by an op expression, followed by some closing parenthesis, followed by a statement. Or it can be other. I'm not sure the purpose of other, but it's like, trust me, there's more. Okay, so op expressions are either this guy, which I'm not necessarily sure where they're going with that. Go ahead.
Look, I'm reading uses that symbol for the null string.
Okay, so maybe they're saying it could be nothing or an expression, possibly. I'm sure we'll see by example pretty quick, but actually that is what it is. Because here's the code example of what this tree used right here. So Scott, right down here we have for, the first op expression is nothing. So they're saying an op expression can be empty or it can be an expression. So then somewhere we need to have a grammar of what an expression is. And we'll see if they give that to us or not. Okay, but in any case, this is the kind of thing we're working with. Now the question is, if this is our tree, and at the top level we have a statement, and then down here we have a statement in this little example. Could this statement right here be something very similar to this one?
Why not?
What is a computer program? We want to really kind of get a definition for a computer program in a Java-like language. So we can start thinking about these in terms of C-style languages, a language like Java, C, C++, Objective-C. If you had to give a definition, a concise definition of what a programming language is in terms of Java, what would you say? And some of the hints are already on the screen we have up here. Go ahead.
Very broad, like kind of like CSM topic is machine ultimately. Parsing, not a parsing engine, but it doesn't accept these symbols.
Okay. So generalistically speaking, true. But I'm talking about specifically a language like Java. So languages like Java are built around the core structure that is a statement. These are statement-based languages, correct? Is it true to say that a Java program is a collection of one or more statements? It's true, correct? If we come up here to that example code they had, I'm just looking at the language of expressions they gave us here. Where's my Java code up here? There we go. So here's our Java program. What is this Java program? It is exactly one statement. Opening, closing curly brace. A Java program is a statement. And a statement may contain other statements. And then some stuff, right? So here's a Java program. We have, let's just call this a block statement. And inside this block statement, we have a var def statement, if you will. How do we know they're statements? Because they have semicolons in them. So here's a statement, here's a statement, here's a statement, here's a statement, here's a statement. Now we have a while statement. How do we know that while is a statement? We don't see a semicolon. All things that end in semicolons are statements, but not all statements end in semicolons. So a while, the syntax for a while is while. This is an op expression. Opening curly brace. Well, the opening curly brace isn't required. What's required is a statement. All of that is a single statement because it's a block statement. And inside this block statement, what do we have? Well, we have a do-while loop. Do-while loops do end in semicolons. That just happens to be another statement. It's a loop, but it's the only one of our three common loops that end in a semicolon. The other ones don't. Why is that? Why do you think the do-while loop they chose to end in a semicolon where a for loop and a while loop do not end in semicolons? Should make pretty good logical sense based on the language. Go ahead.
The statement goes first.
So statement goes first.
Well,
I think you might be onto something. Go ahead. Keep going.
That's because like do this statement while the operator.
Okay. With a for loop and a while loop, because the statement portion of it comes last, we can end on a statement. All we have to do is, we know we're at the end because we detected the statement. But with a do loop, a do while loop, the statement comes in the middle. So we actually have, the syntax kind of makes a sandwich. You have the word do, followed by a statement, followed by the rest of the syntax for the do while statement. And the rest of the syntax is the word while, followed by opening parenthesis, followed by an op expression, followed by a closing parenthesis, followed by a semicolon. That tells us we're at the end of that do while statement. Does that make sense? Where we can detect the end of a for loop statement or a while loop statement by the end of the statement that is the body of those loops. Okay, so when we think about Java, a Java program is probably one big statement. It might be one small statement. It might be one empty statement. So technically, by this thing, could we have a Java program that literally is an opening curly brace followed by a closing curly brace? Is that a Java program? Technically, it won't do anything. In fact, anything we have here isn't even accounting for that our phrase that all programs begin and end with main, right? Remember that guy? That comes down to runtime. So at the compile time, we're going to say, well, this is what we're going to do. We're going to mold this thing into some sort of form factor that makes sense. And then somewhere somebody's got to write the Java runtime environment, and that has to determine how to interpret the Java bytecode that Java compiler spit out. Make sense? Okay, so already we're right back to where we were last semester. We're dealing with the exact same crap. We're dealing with symbols. We're dealing with grammars. It's all the same stuff. Except now we don't have scheme to get the cars and critters and all that stuff. Now we have to write parsers to pull out one character at a time and create tokens out of those streams. Kind of becomes interesting. Okay, so we want to wrap our mind around is what is a programming language? A programming language is a statement. I think we can believe that for this class if we think in terms of C-style languages, okay? Which is what we want to do. Notice they're giving us some, this is up a little bit higher than where we were before, but just as an example, so the punchline we're getting to here is what we're looking at right here is probably a portion of a syntax tree. Okay, so somewhere in here we have an expression. And what is that expression? Notice the expressions are the terminals. And then leafs. So the top level nodes are what is this? And then inside that we have the value. So an expression can be an expression followed by a plus sign followed by a term. Or what's a term? Well, we'll see terms here later. Followed by an opening curly brace, followed by a print, followed by a plus sign. So we have a bunch of expressions that for plus and minus. And then we have an expression being just a term where a term is a 0, 1, a 2, any of those things. Okay, so back to here. We had our step one. Step one is create the top level node, then put the other dudes underneath. Find the next node at which a subtree is to be constructed. Typically the leftmost unexpanded non-terminal of the tree. Well, what does that mean? we're going to create a subtree out of a single statement. A statement will be a tree in and of itself. It might be the most top level statement, because all Java programs are a statement in and of themselves, right? But this could be a statement somewhere inside of this single tree. So inside of this guy, we have a bunch of terminals, followed by another statement. And off this guy, we might have a whole bunch of stuff branching off of him. For some grammars, the above steps can be implemented during a single left to right scan of the input string. The current terminal being scanned is in the input is frequently referred to as the look ahead symbol. So this gets back to that, if we look one symbol ahead, one token by our current language ahead, we might be able to make some determinations of how do we add this to our tree next, based on what the grammar of our language currently says. Initially, the terminal 4 is the look ahead symbol. And for the known part of the parse tree consists of the root. And the known part of the parse tree consists of the root, labeled with the starting non-terminal statement. The objective is to construct the remainder of the parse tree in such a way that the string generated by the parse tree matches the input string. So parse trees go both ways. We can go from a string to a parse tree. We can go from a parse tree back to a string. Those guys should match each other. That's the litmus test for an accurate parse tree. Does that make sense? Okay. So if we took this guy and processed it, we should get the exact same output as if we took this guy and parsed it into our tree. For a match to occur, the non-terminal statement must derive a string that starts with the look-ahead symbol 4. In the grammar, which is that I think farther down we were looking at a second ago, there is one production for statement that can derive such a string. We only have one statement that looks like a 4, right? Whatever. Trust me, it's right. So I want to finish this little section here real quick. So we select it and construct the children of the root, labeled with the symbols in the production. So we can actually start pre-filling out our tree based on what the grammar says it should be. And this gets back to something Beaker brought up last class. Are we checking for syntactic accuracy at this point, or are we just breaking into a tree? This is where the two start intertwining. Because if we start building our tree expecting correct syntax, and then don't find correct syntax, now we can scream. That make sense? Okay. So, each of the 3 snapshots has arrows marking the look-ahead symbol and the input in the node in the parse tree that is being constructed, or being considered. Once children are constructed in a node, we next consider the leftmost child. Just like we did before, we start with the leftmost, start with the leftmost. Now we have his child, which is this expected syntax. The expected syntax was an op expression, and that op expression broke down into one of the forms of an op expression, which is either null or an expression. Make sense? Okay, so what we want to take out of today, I know we're out of time, is programming languages are one big statement. Therefore, your syntax tree will be one big tree. And this is only true, well, this is true for us because we're using a C-style language, which is actually evidence as to why C looks the way it looks. Chicken or the egg type problem. Because it's a semicolon divided up language. All right, I'll see everybody on Wednesday.